Okay, so let's have a look at the reaction between hydrogen and chlorine. Okay, so what we've got here is one molecule of hydrogen reacting with one molecule of chlorine to produce two molecules of hydrogen chloride. Now what we want to have a look at is actually the bonds between them. Okay, so on the left hand side, what we have here is a bond between the hydrogen molecule and a bond between this chlorine molecule, or between the atoms in the chlorine molecule. And that forms a hydrogen chloride molecule. So there's a bond between the hydrogen and chlorine, and we form two of that molecule. Now, when we look at bond energies, we have to use a bond energy data table. And each bond, so the hydrogen-hydrogen bond, for instance, in order to break that bond, we have to put in 436 kilojoules per mole of energy. So on the left-hand side here, this is the side where we break bonds. And then on the right-hand side, after the arrow, this is the side where we make new bonds. Now, when we make a bond, energy is released. Okay, so what we're going to do is we're going to use the data table, and we're actually going to have a look at the total energy that we need to break the bonds on this left-hand side, and then the total energy that we need to make these new bonds. So if we look at this, we go through this each molecule at a time. So we're going to start off with hydrogen, and we can see that we have one hydrogen molecule, and the energy required to break that hydrogen bond is 436. That's kilojoules per mole. Now we've also got on the left hand side a chlorine molecule. So again, we need energy to break that chlorine atom bond. So we'll write that here. And the energy to do this is 242 kilojoules per mole. So on the left hand side now, because we've got no other molecules, and also we haven't got the large numbers in front of these two molecules, and that's for balancing the equation. So what we can do now is do the sum of those two bond energies, and that comes out as 678 kilojoules per mole. And that's how much energy we have to put in to break those two molecules. Right, let's move over to the right hand side now. And over here we've got a hydrogen chlorine bond. And the energy that we need to put in to make that new bond is 431 kilojoules per mole. However, what have we got here? Well, we've got two molecules of this, so we have to account for that in this calculation. So we have to multiply that 431 by 2. And once we put that into our calculators, that comes out at 862 kilojoules per mole. Now, in this particular equation, there's only one product formed. Obviously, in some other equations, we could have other products, and you'd have to do the sum of those on this right-hand side, okay? So on the left-hand side with the bond breaking, we have 678, and on the bond making side, we've got 862. So in terms of calculating the energy change, that is equal to bond breaking take away bond making. So we go over here to the bond breaking side. So in this case, we've got 678 kilojoules per mole, and we're taking away the bond making, and in this case, it's 862 kilojoules per mole. And when you put that into your calculator, that comes out as negative 184 kilojoules per mole. Now, don't worry that you get a negative sign here, because that is really important. So previously we had a look at exo and endothermic reactions. Now, what we found out is that exothermic reactions, they're the reactions that give out energy, have negative values, and endothermic reactions, that's where we have to put energy in, have positive values. So what we can now do is look at the final energy change for this particular reaction, and we'll see that we've got a negative value, and that means that this particular reaction is exothermic. So that means in this reaction between hydrogen and chlorine, we'd actually feel, if we had measure the temperature surrounding this reaction, there'd be a temperature increase. Energy would be released, energy would be given out. And that's because the energy in terms of making bonds is greater than the energy to break those bonds. We have to put less energy in to break than the energy released in making new bonds. So overall, it's an exothermic reaction. Now, when we are looking at calculating bond energy, there's a few things that we need to be careful of that might trip you up. So I'm going to just go through a few things with you. So things to look out for. The first thing to look out for are multiple bonds in a molecule. So what do I mean by this? Well, if you had, because we just had a look at quite simple molecules, but if we looked at something slightly more complex and looked at ethane, so ethane has 2 carbons and it's surrounded by 6 hydrogens. So in ethane, for instance, we've got 2 types of bond going on here. So I'm just going to change my pen colour and highlight those. We've actually got carbon-hydrogen bonds, and for this one we've got 1, 2, 3, 4, 5, 6. So there's 6 carbon-hydrogen bonds. So you'd write that, your carbon-hydrogen, and that would equal 6 times the value for breaking that carbon-hydrogen bond. But we've also got, this is what you need to look out for, and if I was you, I would highlight or circle each bond as I go round and I count them up. But in the middle here, and again I'll change colour to show you that we actually have a carbon-carbon bond as well in the middle. Sorry, that's not very clear in that pink, but we have a carbon-carbon bond as well, and we've only got one of those. So again, you'd look at the value of a carbon-carbon bond and multiply that by 1. Well, obviously it would just be that number. So that's something to take care of. Now the other thing I'd also say to you is look carefully at the balanced equation, because actually at the start of each of these compounds, these molecules, you could have a balancing number as well. So if this was 2 ethanes react with, I don't know, 1 oxygen, then you'd have to multiply up those number of bonds accordingly. So now instead of having 6 times that carbon-hydrogen bond, we'd actually have 12. And for the carbon-carbon, we'd now have 2. So that's something to take care of, okay? So that was my second point. Look out for balanced equations. Now, the other thing I'd look out for is, and this really comes up under the first point about multiple bonds, but things like carbon dioxide. So this is what a molecule of carbon dioxide looks like, and we know this is CO2. So when we're counting the bonds for this one, just be careful, because it's obvious that there's a CO bond and it's a C double bond O as well. But actually in one molecule of carbon dioxide, there's 2 of those. Okay, so there will always be a minimum of 2 times whatever the value is for the carbon double bond oxygen bond energy. And again, look out in your balanced equation, because at the start of carbon dioxide, that could have a 3 in front of it. So again, instead of just having 2, this time you would have 6 carbon-oxygen bonds. Okay, so again, just highlight as you go through, draw the molecules out, highlight them as you count them, then look out for the balancing. Don't forget that on the left-hand side, you write down the total amount of bonds broken, and then on the right-hand side of an equation, it's the total amount of bonds made, and it'll be bonds broken, take away bonds made, and that will give you the overall energy change. I hope that helps. Thank you.